Osmosis is one special type of passive transport facilitated diffusion across the membrane. So it gets its own lecture. It also will be part of the focus of lab. And it's kind of a tricky thing for students. What you got to do is draw it out, write it out, explain it yourself to someone else. And you got to think through it. Some people comes quicker. Some people just needs practice, right? So let's do it. What is osmosis, first of all? It's the movement of water across a membrane. And water can move from high to low concentration as well. But water, if you remember, is the solvent. So typically we talk about solute moving. So glucose or proteins not moving usually, salts, those are the solutes. The solvent is water in our cells, in our bodies, and those together make a solution. So most solutes that dissolve in water, many of them can't pass across the membrane very easily. Salt, NaCl, sugar, large proteins. If they can, that's either simple or facilitated diffusion. When solutes can't move down their concentration gradients, water will move instead, or also in reality. And this is super important for our physiology, the movement of water across membranes. So it's something that we'll come back to, especially in the spring. So water moves from low solute concentration to high solute concentration, if that works for you, or water moves from high water concentration to low water concentration. So here is an example. Where is my spotlight? Okay, so here's an example of a semi-permeable membrane. There's two compartments here. Here's one compartment, here's the other, and there's a lipid bilayer. So no membrane proteins. We're just talking about what can move across this membrane. Water is our solvent, and glucose is our solute. Can glucose move across the membrane very well? No. There is a drive for glucose. There's unequal concentrations across this membrane. So if glucose could, it would move which direction? Left, right? Left, right. It would move from high concentration to low concentration, down its gradient. That's what's spontaneous. That is simple diffusion. That cannot happen because of this membrane. It's selectively permeable. So instead, there still is that drive though. There's a force there. That is actually an osmotic gradient. So an osmotic gradient exists between these two solutions. And it's going to happen every time you have a membrane that is not permeable to some solute, which is pretty much all the time, to different extents then. So what's going to happen is water is going to move from low solute concentration to high solute concentration. One way of thinking about it, it's going to dilute down this sugar over here. Or you can think about it, these H2O is a molecule. These molecules are in higher concentration here than they are over here. Either way you want to think about it, right? It's the same thing, same direction. Either way, water is going to move from this side to this side. So you actually will have a higher water level over here. And this is actually equilibrium because of that osmotic pressure. So this term osmosis is a type of diffusion involving the net movement of the solvent molecules opposed to solute across a semi-permeable membrane from an area of high water / low solute to an area of low water / high solute. And again, it's the tendency to reach equilibrium is what's driving this. Another term that we'll not use a whole lot until the spring, but for some people, if you like numbers, osmolarity can help you understand this. So I want to do the same example, but using numbers here. So osmolarity refers to the total concentration of solutes in a solution. So a high osmolarity solution would be something with a lot of sugars and salts in it. This is something your urine, just as a visual example, when you're very dehydrated, you produce very high concentrated urine that's going to have high osmolarity. It has a lot of sugars and salts per volume of water in your urine. When you chug 2 gallons of water, you're going to urinate out very low osmolarity, clear and copious urine. So the total concentration of solutes is osmolarity. So it's in milliosmoles, and again, we'll be using this more in the spring, but here, if numbers help you, we can apply that to the same scenario. So here we've got some solute in low concentration, some solute in high concentration. And we actually have numbers to that now. So 200 milliosmoles is the lower, 300 milliosmoles is higher. That's actually the concentration of our plasma, our blood. And water is going to move from this direction to this direction. Like we said in the previous slide, low solute concentration to high solute concentration, high water concentration to low water concentration. Low osmolarity to high osmolarity. So only worry about this if it helps you. So what that's going to look like is this, same as the previous one, but what's different about this example is here now we've got these numbers that might help you. So osmolarity is now equal on the 2 compartments. This is equilibrium, right? So now it's stable. That's why there is a drive here. There's not a drive here anymore, even though the volume difference is different, the osmolarity is not. And that's why osmolarity maybe is helpful, because that's what is in equilibrium. And that's what's going to be important for the urinary system in the spring, is it's all about reaching equilibrium, and that drives water movement to regulate our blood volume, and it's all awesome. Okay, so one last thing, I think I have, yep, that show up there. So this is osmolarity that I just talked about. This semester we'll be talking about tonicity. It's annoying. Tonicity is basic. It's not the same thing as osmolarity, but we're not really going to discuss the different. Tonicity has to do with the permeability of the membrane. So we'll be using hyper and hypotonic. Come back to that in a moment. Here is another example. I included this because it introduces the idea of hydrostatic pressure. Don't need to know about this yet. If you want to know more, go to this website, read. If you're a physics person, read all about this. I'm going to skip this for now. Okay, let's get back to the tonicity. There's a lot on the slide. Just hold up. So this is why this type of thing matters for our cells. Water movement matters for a urinary system, but also for our cells to be happy. So isotonic is where I want to start here. Isotonic, iso is the same. This one is isotonic. So there's equal concentration of, equal osmolarity, concentration of solutes inside the cell and outside the cell. These arrows represent movement back and forth across the membrane of water. Remember, so water can move, not solutes in this situation. No change, happy cell. This is a very simplified schematic of a cell, right? Without anything in it. Isotonic. What happens if we have something that is hypertonic? Inside, actually, let me undo that. The outside is hypotonic. So there's low concentration of solute outside. The inside is hypertonic. So this is a relative thing. Typically you talk about the solution you're putting something into. So we're putting this cell into a hypotonic solution. Hypotonic is fairly synonymous to hypoosmotic, low solute concentration. Again, the difference is tonicity refers to the permeability of the membrane in there as well, and we're just going to assume the membrane is not permeable to this solute. What happens if you put a cell inside a hypotonic solution, so artificially or for real? You're going to have water move inside the cell. The water is moving from low to high solute concentration. The water is moving from high to low water concentration. What's going to happen? Water is flowing into the cells. The cell is going to burst. Vesicle here is what they're calling this cell. In a moment here, I've got cell examples. This vesicle here is the same as a very simple cell. Then lastly, we've got the outside hypertonic. So we throw the cell or vesicle into a high concentration, high solute concentration solution, a hypertonic, hyper compared to the inside of the cell. What's going to happen? The water is going to flow out, and that cell is going to shrink. You can see for this, you need to practice, right? Hypo, hyper, and then where's water going to move? Be very deliberate about labeling, being clear about what is high compared to what. Hyper, hyper, hypo, low, knowing those terms. Last thing here is putting this onto, so actually this happens to red blood cells. So this is what it would look like in terms of a red blood cell. Isotonic, happy red blood cell, so this would be in your blood plasma. Hypotonic, red blood cell is going to swell and potentially burst. And then a hypertonic solution, the red blood cell is going to shrink or crenate. And we will see this in lab. Okay, let's do a learning check. So what I want you to do is imagine what you're going to do in lab. Add red blood cells to a vial of distilled water. Distilled because that means there's going to be no solutes in it. The figure below shows a single red blood cell in this water. So a kind of schematic of this. Indicate on this diagram where the solutes are high and where they're low. And then tell me, is the external solution hypo or hypertonic compared to inside the cells? Which way will water move, and what will happen to the red blood cell? So pause the video and do this. Okay, high solutes inside the cell, low outside, right? It's distilled water, and inside a cell, you got a bunch of stuff. In reality, it's salts, sugars, proteins, all that stuff. None of it can move across the membrane. So the external solution is hypotonic compared to the cells, lower solute concentration. What's going to happen? Water's going to move into the cell and potentially have them expand and potentially burst. I'm going to go ahead and open up this other practice website here. It's something you can read more about and practice as well, but there's one practice question on here that I want to have us do. So we are going to answer this question right here. There is a container here. It's probably a little small. Solution A, solution B, separated by a membrane that allows water to pass through, but not any solutes. Over here, solution A, there is protein albumin, a large protein. Over here, solution B, there's glucose. 3 molecules of protein, 15 molecules of glucose. Which way will water flow? It's going to move to the right because this has a higher osmolarity or higher tonicity. It's hypertonic. What matters is the number of particles. I like this example because there's 3 large proteins here that still counts as only 3. That's what osmolarity, the concentration of solutes, means. Doesn't matter how big they are, osmotic flow depends only on the concentration of the particles, not the size of the particles. Okay, so what we've done here, oh, sorry, I wanted to remind you that aquaporin is a protein that helps water move. So it can move across the membrane on its own. Water can, to some extent, but aquaporin is enabling facilitated diffusion to allow for more water to cross across the membrane than otherwise could. So when aquaporin is present, it would be an example of facilitated diffusion. And a reminder here, aquaporin is a what kind of protein? Transmembrane. Just told you this, but you should know it. Water movement through aquaporin is an example of simple facilitated active transport. Facilitated diffusion. Again, water can also use simple diffusion, but in this case, it's using facilitated.